Have you ever wondered how electrical engineers know exactly how voltage behaves inside a circuit? Even when circuits become complex and contain resistors, coils, and capacitors, engineers can still calculate every voltage in the loop. One of the most important tools that allow us to do this is Kirchhoff's voltage law, also called KVL. My name is Jana Hamed, and this is my ENGG104 presentation on Kirchhoff's voltage law in AC circuits. In this video, I will explain what KVL is, how KVL works in DC circuit, how KVL works in AC circuit, the difference between them, and finally, I'll solve two examples including an AC circuit with a resistor, coil, and capacitor. So first, what is KVL? KVL stands for Kirchhoff's voltage law. It states that the algebraic sum of all voltages around any closed loop in a circuit equals 0. This means that the total voltage supplied by the source must equal the total voltage drops in the circuit. The reason for this is the law of conservation of energy, which means energy cannot be created or destroyed in a circuit. In DC circuits, voltage and current are constant, meaning they don't change with time. Because of this, voltages can be added using simple arithmetic. To calculate voltage drops, we use Ohm's law, V equals IR. Example. Suppose we have a 12-volt source and two resistors connected in series. First, we apply KVL. Using Ohm's law, then we substitute the values, we solve for the current, and now we calculate the voltage drops. Voltage across resistor 1, voltage across resistor 2, and finally we verify KVL. The law is satisfied. In AC circuits, voltage and current change continuously with time, meaning voltages cannot be added directly like in DC circuits. Instead, AC circuits use phasors and impedance. The AC form of KVL is written as: in AC circuits, Ohm's law becomes V equals IZ, where Z represents the impedance. Impedance is the opposition to current in AC circuits. Each component has a different impedance. For a resistor, ZR is equal to R. For an inductor, also called a coil, ZL is equal to omega L. For a capacitor, ZC is equal to 1 over omega C, where omega is the angular speed, which is equal to 2 pi f, and J represents the imaginary number. Example. Suppose we have a series circuit containing voltage source V equals 120 volts, frequency of 60 Hz, resistor of 40 ohm, inductor coil of 0.15 henries, and capacitor of 18 microfarads. Step 1, we calculate the angular frequency, which is omega equal to 2 pi f. We have 2 pi 60, so we have omega equals to 377 rad per second. Step 2, we calculate the reactances. The inductive reactance is equal to omega L, and the capacitive reactance at C equals to 1 over omega C. Step 3, we calculate the total impedance, where Z is equal to R plus the inductive reactance minus the capacitive reactance. Therefore, the magnitude of impedances is given by this equation. Step 4, we calculate the current using AC Ohm's law. I equals to V over impedance. Step 5, we calculate the voltage drops, voltage across the resistor, across the inductor, and across the capacitor. Applying KVL, so KVL is satisfied. To conclude, Kirchhoff's voltage law states that the sum of voltages around a closed loop is 0. In DC circuits, we use resistance and Ohm's law. In AC circuits, we use impedance and phasors because voltages have both magnitude and phase. Even though the calculations are different, KVL remains one of the most important laws used to analyze electrical circuits.